All right, hello and welcome to week 43 of Chill Kernel Hacking for Fun. Thanks a lot for joining and for being here. Today we are going to continue with this MIT course, the 6.828 operating systems course, which I've been doing for like a year now. And we are working on user mode page fault handling. Give me just a second to make sure the stream is going correctly and that all my tweets and stuff also posts quickly in the Discord. But yeah, user mode page fault handling. This is going to be a pretty good stream. At least I'm looking forward to it because we're going to write a bit of assembly today, which is always a bit challenging, but quite exciting when we get the chance to do it. Okay, Discord streaming now, running some assembly. Almost there. All right, let's see. Test 0. All right, cool. Looks like our chat is working successfully. So I think we're all set up. Anything last minute to do? I don't think so. Yo, what's up, Cat Flare? Thank you for joining. It's been a while. Hope you're doing well. Yeah, I'm pretty stoked. We're working on user mode page fault handling today. And I've already started this a little bit, actually. And specifically, we're working on exercise 10, which is the assembly routine that will take care of calling the C page fault handler and resuming execution at the original faulting instruction. Not much been coding my kernel and doing school stuff. That's how you're doing. Cool. Yeah, I'm doing well, thanks. Yeah, I'm feeling pretty good about this project. This kernel programming, for a long time I was debugging stuff and it wasn't super fun and it was very challenging, so I'm glad to be back doing some actual development. Hey, what's up, Lizard? What's up, Zabriel? Awesome, we got a bump in chat today. Thanks all for joining. Hope you're doing well, Lizard. Feel free to check in on how you're doing. Yeah, I'm doing well. Catfire, your kernel, you're doing your kernel. I would love to hear how your kernel is doing and what you're working on with it. Yeah. Yeah, lately I've just been doing all these exercises, which is like multi-core support, and working on the fork system call, basically. And for some reason, this class does fork in userspace, which is very interesting. And so rather than having fork be implemented in the kernel, we instead expose a bunch of these kind of very small system calls, which allows us to implement fork in userspace, which is kind of an interesting design that I wasn't expecting. Exploring the STM32. Word, cool. That's cool that you do all that hardware stuff with the FPGAs and microcontrollers and stuff like this. I find that pretty awesome. Yeah. Yeah, today, okay, let's just get into it. I'm super excited about this. So yeah, and in terms of the order of things, next week is going to be a pre-recorded stream. And so actually what I'm working on right now is following on from what I've done in this pre-recorded session. And so if you want to see a bit of the background behind what I'm doing right now, it'll be available in the stream. That'll be next week. Implement the physical memory allocator, virtual memory, C++ runtime, heap, ACPI, SMBIOS, APIC, IOPIC, PCIe. Crazy. That's awesome. I honestly don't know half of those words, but that's awesome. Sounds like you're doing a lot of hardware support. Also PCIe sounds awesome. Okay. User mode page file entry point. So as usual, let's take a look at Git, what has been happening in the Git world. So I spent a long time implementing all these system calls that allow us to have a working user space fork, and that was working. And then in episode 44, which will be released next week, that's when I implement this thing. It's a system call for beginning support for user space page fault handling. And so consistently with this whole theme of trying to do a bunch of stuff in user space, what we're actually doing, it seems, is implementing copy on write in user space, which is pretty interesting. And part of doing that, part of implementing copy on write fork in user space requires user space to be able to handle page faults. And that's what we're doing. And so the idea is that user space is going to be running, and user space is going to be able to pass a function pointer to the kernel that will get called whenever there is a page fault that is triggered by the user space process. And so the user space process is running, it registers with the kernel this function pointer, then later on somewhere in the program, it's going to touch some memory that has been basically shared between two processes. And so it's going to touch the memory that does not have the writable bit set on it. It's going to try to write to some memory that does not have the writable bit, which is going to cause a page fault from the CPU. And instead of handling that page fault in kernel space, the kernel is going to basically defer back to user space for how to handle this page fault. And what it's going to do is the kernel is going to call that function pointer that previously was given to it by user space. And that's a bit of what I was doing in the pre-recorded session that will be available next week as episode 44. Here is the system call that allows us to register the function pointer with the kernel. It's very simple. The user space just passes in a function pointer. The kernel user space can pass a function pointer actually for a given process. The kernel looks up the process data structure and then simply just saves that function pointer into the task state for that process. That's pretty straightforward. What I also implemented in the pre-recorded session, which will be available next week, is executing the user space page fault handler. This was a bit more involved because I'm just going to turn off the side mode. This was a bit more involved because we're here in the page fault handler of the kernel, the kernel's native page fault handler. And the kernel is going to first check if a function pointer has been given to it by user space. And if we don't have one, we fail out. Next, we look up the we look up this area of memory in the process called UX stack. So user space is responsible for allocating its own stack for this handler to run on ahead of time. That's user space's responsibility. And so we check that the stack exists and is writable. So we've made sure where there is a function pointer given to us, we've made sure that user space has a page fault handling stack available. There's a little bit of code that handles whether the stack is being overflowed because if the fault address is off the end of the stack, basically, actually, I'm actually looking at whether this is correct. Did overflow exception stack. Let me think for 1 second. This actually seems a little bit suspicious. If the fault VA, let me bring up the old memory layout. Which is right here. I see. So what we're watching for is, was there a page fault that happened in this region between the normal stack and the user exception stack? What we're expecting is that if there was a stack overflow, there's going to be a memory access that is a little bit past this border. It's going to be a little bit lower than the bottom of the user exception stack. And my check is saying if the fault virtual address is greater than or equal to uStackTop, and it is less than uStackTop plus page size, so it is in this region, then we overflowed. So I believe that actually looks right. If we overflowed, we fail and we kill the process. There's a bit of handling here for handling recursion. So if userspace page faults while in the process of handling a page fault, and what that means is, okay, so userspace's function pointer gets called to handle a page fault, and then while running code there, it triggers another page fault. We are actually going to handle this, and there's a bit of code to handle that recursion. We are actually going to, the kernel is going to receive another native page fault, and we're going to handle that, and call the handler again, basically with a second exception stack frame or user page fault frame. We're going to write a bunch of information about the page fault into user space on this stack frame, so user space can access some of the information about the page fault. And then we're going to arrange for the user space handler to execute. And what we're going to do is we're going to point EIP at this function pointer, and we're going to point ESP right at the bottom of this user space trap frame structure that we have written into user space. And then we're going to drop back and run the process. And so that was a summary. That brings us to what we're doing today, which is here. So now we're implementing the user space component of this. And the user space component of this is that function pointer that gets passed to the kernel. It's directly the code that is going to execute when the kernel triggers the user space handler. These are literally the first instructions. So what's going to happen is we're going to push ESP onto the stack and then call the actual C handler, which I'm not actually sure if it exists right now, but we can see the function prototype. It's a void function that takes a utrap frame as a pointer argument, and that's what we do when we push ESP. So the utrap frame is written into memory onto the stack. We're going to push a pointer that points directly at that, and then call this function, which we do with call EAX. And then after that's finished handling, we're done and it's time to return back to the original user code that was executing at the time of the page fault. What we do is we repair the stack because we pushed on the ESP, so we're going to undo that operation. And now it's time to return back to the real running state of the program. Either the first situation is that we're simply returning back to the actual original non-handler execution flow that triggered the original page fault. But the other possibility is that we are kind of unwinding the recursion stack and returning back to a previous execution of the page fault handler. And we need to handle both of these. All right. And the way we're going to do this basically is we have all this information in the U-trap frame actually. We have all this information, and what we need to do is we need to return execution to EIP and then also reset the stack to ESP. And if we do that, we're going to resume execution of whatever previous state was. Yo, Digitalize, what's up? Nice to see you again. Hope you're doing well. Okay, I'm just gonna stop talking and get to work. Okay, I sketched this out a little bit last time, but we have a little bit of a challenge here because as we're writing this assembly that restores the state of the process, there's various constraints that we accrue, basically. So after restoring all of the general purpose registers, we can no longer use any general purpose registers, otherwise we'll clobber them. After returning E flags, we can no longer do any math or branch or anything that involves E flags. And so those are some constraints. And then the last things we need to do are swap the stack pointer back to point at the EIP we just pushed, and then trigger a return instruction, which is going to pop that EIP off the stack, point EIP at that address, and also put the stack back into the exact location that it was at the time of the original user space code execution or the previous state of running the fault handler. And I have kind of sketched out how I'm going to do this. I definitely might need some help from ChatGPT here to actually know the assembly code to type, but I know in principle what I want to do. So my idea was the first thing we're going to want to do is place EIP into memory where we need it. And this is the C pseudocode of what I want to achieve. I want to write at UTF ESP -4 the value of UTF EIP. I am going to ask ChatGPT how to do this. Okay. How do I do this in ATT x8632 syntax? What? That would be so sick if I could. Wow. So we need to put this located in a base register. is pointed at by ESP. Can we do this more tersely? Yeah, I'm trying to use these offsets. So load EIP into EAX. No, but it got it wrong. The parentheses reg is offset. And so this is saying take the ESP register and move the value that is plus 4 bytes, like add 4 bytes to the value of ESP, read like a long, which is 4 bytes, I believe, from there, and then move that into EAX. But this is kind of wrong, but whatever. Maybe I'm being kind of too lazy here. Maybe I should be a bit brave. The third instruction. Okay, I see. This means dereference. Move EAX into the place in memory that is pointed to by ESP. I think I'm just being too lazy though. Let me try to do this. Okay, so I'm trying to, there's like a very naive way to do this, which is to use a lot of intermediate registers. Like what I'm kind of intuitively envisioning is a more terse way of doing this, where we don't need to, where we just like, it's kind of it. We don't like, it's less of this storing things in intermediate registers and more just directly expressing memory operations. Like basically there's a single memory write that I want to do here. I want to write UTF. So I'm just going to guess. Man, I really wish I was using Intel syntax, which I know like a little bit better. So ESP points here. So we're going to need wait a sec. Okay, so this is like a kind of a big offset. Shoot from the instruction set. I'm going to actually low-key start a debugging session, because I find it can be useful. Oh, what? Oh shit, I can't, I need to comment this out. All right, this is, okay, we're gonna, does it build? Also pop FD. What do you mean there's no pop FD? Full Intel manual. It's again, this kind of confusing thing. I could have sworn it's called pop FD. Push. Okay, what am I trying to, I'm just gonna Google it, or I'm gonna chat. No, I'm gonna be old school. x86 pop back into E flags. Pop FD, that's what I thought. Pop a dual from the stack and stores the value in E flags. So pop FD, AT&T syntax, gas maybe? Okay, what if I, yeah, here we go. These are the real push FL. Dang. Being flagged as illegal. That's what I'm saying. That's what I'm saying. Come on. I could just ask ChatGPT. Okay. These are valid only in Intel syntax by default, using which are, these objects are spelled push F and pop F. All right, this is worth tracking in the Miro. All right, so it's pop F. All right, do we build? We build. So low key, I'm going to start that debugging session just so I can print the size of push regs. Or struct push regs? 32. That's literally the one. That's like kind of what I do if I want to get the size of a structure. It's often easiest to just like open a debugger. I'm just gonna maybe verify that. I mean, it's not too hard. It's like 1, 2, 3, 4, 5, 6, 7, 8 times 4 is 32. Okay, so yeah, so it's 32. So this thing is 32 bytes. This stuff is 8 bytes. So EIP is going to be at offset 40. So that means this is going to be something like 40? You know, just to test this out, I'm going to load this into EAX and just see if this even compiles. Say marked as a duplicate before Stack Overflow. Yeah, for 2002. So is that what you mean by before Stack Overflow? I will, thank you very much. Okay, does this build? You know, what I really want to do is look at what file am I even modifying? It's a pf entry. Dang. Oh, but this is in like lib. Pf entry. Oh shit, that's, oh man, I don't have assembly files. 5386 elf objdump.d intel pfentry.o. Right, that's actually like a very small amount of assembly code, right? Okay, what is going on? I do not like what I'm seeing here with the DS. What am I seeing? Oh, that stands for an unresolved symbol. Okay. And I call add move ESP is x28 40. Okay, good. So that is looking good. That is the instruction I wanted. Good. So the stupidest way to do this so that's this. EIP plus 32 plus 8 gets us to EIP. We're trying to load that into the memory that's pointed to by what, 40 plus 8 is 40. What's the size? Does this work still? Okay. Uint pointer t is 4 bytes. Also, uint pointer t 4 bytes also, right? So 40 plus another 8 is 48. So actually, this is what I was hoping to be able to do. I don't too many memory reference for move. That's right. Okay, that's why I guess ChatGPT did not propose that, because you cannot actually have 2 memory references in a single instruction apparently. So I need to store this in a register. Is that right? I load EIP into EAX, then I take EAX and I write it, but into ESP -4. So so right now it's not correct because I'm writing it, I believe directly where ESP points to. Does this work? I'd be very surprised. Does this work? It does. We're going to refresh. It's 30, 48. So we're loading. Yeah. Intel operates like kind of the right thing goes into the left thing. So we're reading from ESP at hex 28, dereferencing that, loading it into EAX, then taking EAX, writing it. I'm just gonna, okay, this is where I'm gonna ask ChatGPT how do I, oops, all right. Equal x86 AT syntax, but do you get what I want? What I want to do though? I'm trying to combine an offset, field offset with an adjustment. Okay, compute the adjusted address in register. Load, see what you, yeah. Load it into EX, subtract 4. Okay. So I could have sworn that x86 supports some like pretty advanced stuff like this, but apparently I'm wrong. Okay. EAX equals UD. I'm just gonna put the pseudocode right here. This is going to be EBX equals UTF ESP. Then I want to do what, like a sub L for EBX, and this equals 4. Then EBX. EBX equals EX, something like this. So we load each of these things into registers. We need to explicitly do this -4 computation, which we do, and then we take EIP and write it into this address. Okay. I think that is approximately the right way to do that. I'm doing that kind of early because after we do this instruction, we can no longer use any general purpose registers. So I need to do that before. There's also a couple other things I need to do before. However, there's a big question mark to do. What about page faults if these pushes overflow the stack? That is a question. So my general idea for what the solution for this is to use memory. So we have this constraint that after doing the pop AL to load all of the register state from memory back into the actual registers, we can no longer use any of the registers to store things, for example, like I'm doing here for these intermediate values. And that's important because later on we're going to need to move a value back into ESP. And the initial naive way to do this is to take the value we want to put into ESP and put that into a register and then move from that register into ESP. But that would mean we would need to clobber and use a general purpose register, which we can't do. So therefore, the only other alternative, or the main other alternative, is to use memory. Rather than putting things into a register and moving from one register to another, we put things into memory and pop into the register, basically. And that's what I'm trying to do here. And so the general approach here is first put this EIP thing where it needs to go ultimately. Because, so just to illustrate a little bit more, the exception stack where we currently are needs to look like this for my solution. The trap time stack where we're returning to needs to look like so the bottom thing, it needs to be EIP to return to and bottom of stack at time the page fault happened. So that's what we're doing here. So this kind of thing is what we are creating with this stuff up here. We are taking the ESP, which points at the ... We're subtracting it by 4 bytes, and we're writing an EIP into there. We're getting that all set up. And then what we're going to do to actually restore execution is like the last 2 instructions we're going to execute are going to be 1, move ESP to point at this EIP. Move the actual ESP register to point here. And then the last instruction is to do a ret. And that pops this EIP into EIP, redirects execution there, and repairs the stack so it points at exactly the same place it was when the user space page fault happened. So that's a general description of the stack that I'm trying to create on the trap time stack. And in order to do this thing where we move ESP to point here and then do the ret without, and in a way that meets all our constraints, is to use memory. And so the way I'm going to do that is I'm going to, on the exception stack, push 2 things. I'm going to push ESP and then E flags. And then after doing that, I'm going to, after that's done, I can achieve what I want to do by executing 3 instructions. And that's it. I can, 1, pop F, which pops the E flags. I can, 2, pop ESP, which pops ESP and points it at this EIP. And then 3, I'll do the ret. So that's my plan. Sorry if that's confusing, but this is like some real low level shit or whatever. So we're finally doing it. And this is actually also kind of the life of an exploit developer. Like this is very similar, like we're not writing a security exploit right now, but this is very similar kind of thinking that you do when you're writing security exploits, because you're often implementing ROP chains and stuff like this and worrying about registers and having all these constraints that you need to abide by for the exploit. So it's actually kind of cool. So that's my current understanding of the solution I want to achieve. I think it should work. I do have one question, which is what about page faults that happen? Because we're going to push stuff on, like we're going to push things into memory. And it's possible that we overflow the stack when we do that. But I think we're just going to get killed by if that happens, which might be totally fine. One second, let me just check, make sure the music is still going. All right, cool. So that's the plan for now, at least. It's actually also kind of a question. What happens if any of these things page fault? I actually don't really know. I mean, that just means I don't think it's possible for this to page fault. Because UTF is pointing at the stack, which should be a safe place. But maybe this memory write could fail because we're writing to ESP. But it's pretty unlikely that ESP points to some like random place. ESP should be pointing to valid stack memory. Yo, what's up, Hector? Nice to see you. Thanks for dropping in. I'm working on user space page fault handling, and specifically we're writing a bit of assembly code that returns back to user space execution after user space handles the page fault. All right, let's just, okay, enough talking. Let's just try this. And so, I wonder, I've done the right, I could technically just do this stack preparation over here too. Prepare stack for later. And I need to do two things. I need to push the ESP. Oh, wait a second. Did I? No. I always get confused about how to read the structs, but wait a sec. Why do I have +8 and +4? I think I was actually reading this incorrectly when I wrote this. Structs, like... Structs start from here and go up in memory like this. So, yeah. So I'm trying to do a push L. First of all, let's push L as an instruction, push L. So first I'm trying to push the ESP value, which is here, which is at the end of the struct. We've actually already read it, but we've subtracted 4. Push TF ESP. We need to push E flags. Wait a sec. 48. This is 44. Can you do this? Push UTF E flags. Does this compile? It does compile. let's check out what our assembly looks like now. So here's the part where we are doing our memory write. We load in EIP from offset 40 to EAX. We load in the ESP from hex 30. We subtract it by 4 and then write the EIP into that slot right under ESP. Then we push the ESP thing, and then we push, I think that works, actually. And then we let it rip. Then we just go ahead and we add 8, because the ESP is pointing here. We add 8 to skip over that. We then do a pop AL to pop all of those registers. Okay, then we do the pop F. Oh, wait a sec. Oh, wait a sec. No, this is wrong, because I don't think. Oh, I see. That's why. Wait, that's why those offsets were so strange, because at this point in execution, a bunch of stuff was already popped off the stack, and the stack pointer is actually pointing right here. So actually, yeah. So that is sort of a reason to actually do this stuff right here after. So it's going to be ESP plus 8 and ESP plus 4. Right, we cannot do this. Yeah, so we call this thing, we do our EIP write into memory. We add ESP plus 8, which skips over these two things. We do the pop A, which pops the registers from the stack into memory. Now our ESP is pointing at the EIP. We do a push of this plus 8 to push the ESP. We do the push at hex plus 4 to push the E flags. We do a pop F to pop the flags. We pop ESP and we ret. And I think that is actually it. And now we have our like very shellcodey looking thing, which is going to return execution back to the user thread. So I'm very excited to try this out. But before that, let's all take a 20-second break to stand up, stretch, and get some water. All right, I'm gonna take a quick social media, I posted this on Blue Sky for the first time today. And because I'm curious about trying that out, because it seems like a lot of people are moving over to there. Got a little bit of engagement. Surprisingly, very little on. I think I'm not getting notifications on Twitter. Okay. Anyway, let's go. Let's try this out. Actually, what do I actually do? How do I try this out? So I think I've implemented exercise 10. Okay, I think I can't actually try this out until I finish exercise 11. So what I will do is commit this. Yeah. Hey Zara, welcome. Thanks for joining. Hope you're having a nice day. All right, I'm going to commit this. I'm just gonna commit. I can get rid of this. Don't need this, don't need this, don't need this. This. Yeah, I think I can get rid of this stuff. Oops. Place. Do this first because we use intermediate registers, so it can't come after the pop A. To restore general purpose registers. Three, set up stack for the following pops and rets. Do this after we restore GPRs, because loading GPRs above requires popping them to be, wow, what, at the bottom of the stack. And here we need to push more things. For execute the rest of the sequence. Pop E flags, pop ESP ret. The nice thing here is that no intermediate registers nor arithmetic are needed. And return to previously executing code. Either the original trap time state or the previous execution of the user page fault handler. Okay, I have added like hella comments and description of what I'm doing because it's kind of involved. And what is this, exercise 10, exercise 10, implement page fault up call. Yo, Moom intro. Mum intro. I don't know how to say this. Hello. Moomin troll. I see. Okay. Yeah, Moomin. Welcome. Thanks for joining. Okay. Let's keep it moving. Finally, you need to implement the C user library side of the user level page fault handling mechanism. Exercise 11. Finish set page fault. What? Page fault.c set page. Okay. Okay. What is this? So this is a C program that userspace is going to use to place, like register their function pointer. I see. The general flow here is that userspace is going to declare its own handler function. It's going to call this libc routine, which simply saves it into a global variable, which is then referenced by that assembly stub we just wrote. So after doing this, this is just userspace. First time through here, what is? Okay, I need to do some stuff there, but this is just userspace. And then userspace triggers the page fault. The kernel gets a page fault, handles it, diverts execution back to userspace at this assembly stub. And then the first thing the stub does is basically call this function pointer, which userspace previously passed in here. Okay, I just need to what is it? Okay, set the page fault handler function. If there isn't one, page fault handler will be 0 because it is what? A global function pointer. The first time we register a handler, we need to allocate an exception stack and tell the kernel to call the assembly language. Okay, I see. Sys page alloc, right? 0 for our, and map a page of memory at ux stack top minus page size with permissions pte writable. What happens if that fails, actually? It can fail in all sorts of ways. It's error, if error, panic, panic, alloc user page fault stack. I'm just gonna panic. I don't know. I don't really know how else to handle that. Stack. And so the first time we allocate the stack. And right, sys this. And we pass in 0 and we pass in page fault up call. So it kind of sounds like page fault up dog. That's kind of what my brain jumps to. Yeah, we pass in the stub here. Can this fail? Probably. I'm just gonna do the easiest way of error handling, which is to panic. failed to set page fault upcall func. Okay. So this is, oh. Okay. That compiles. Yeah, I think that's it too. Serve size impl set page fault handler. Okay. Moment of truth. Moment of truth. Okay. Here for the streak. Woo. Yeah, what's up, off 9? Yeah, good job on keeping up your streak. I appreciate that. Make. I don't even know if this works. Like, does my make file even do this? Did it work? I feel like it worked. You should see new end, blah, blah, blah. User fault, VA, blah, blah, blah. Trap frame, blah, blah, blah. I think that worked, to be honest. Let's take a look at user read. What's this thing? Fault read. Buggy program faults with a read from location 0. So yeah, this thing does a null pointer. But wait a second, does it? Lib main. Where? It's like set. No, what is this thing called? Set page fault handler. Where is this called? So there's no, oh wait, user fault VA. So this doesn't really involve any of this. All this tests is that we're just executing this code. That's literally it, because the fault read program doesn't set up anything. It doesn't have a trap handler, and it doesn't call the registration function. So it just is not ready at all to do user space page fault handling. So all the code that this is running is the error path. And so in particular, it's erroring out on this first one, I believe, because it didn't pass a function pointer. That's good news though. That did not crash or anything. So it didn't run a lot of code, but fault, what, die? Okay, this is getting into it. We are oh. Faulted at VA, dead beef, error 6. Dang. All right, that did not work. Time to start debugging. Time to start debugging. Failed to alloc user page fault stack. What are you talking about? Fault die. So clearly something did not work. So clearly, does this even work? Don't panic. I have no idea if this even works, but I'm just gonna try. -3. It's kind of cool that I can just directly jump around. Okay. One, two, three, E inval. That is interesting. Why? Did I do something wrong here? -3. What if I add PTE P, PTE U? I don't think this should make a difference, but I wonder if it does. Yeah, that worked. Holy crap, that worked. So why was it necessary to put all these things? I just want to investigate that. Yo, what's up, Sarav? Yo, bro. What's up, man? So I am just curious. Do we get an 11? Two, 2, 1, 1. So it's not the VA, it's the has valid perms. Man, and I spend so much time unit testing that function too. What? Oh wait, PT and PTE must be set. I see. Oh, that's very obvious. I just misread that. PTEU and PTEP must be set. PTE avail and PTE may or may not be set. No other bits may be set. And has valid perms. It's gonna fail if mandatory bits are set. I see. Okay. Okay, good stuff. So I just called it incorrectly. What's up, Sarav? What's this thing you're doing, finding 0 day? I'm not finding 0 day at the moment. I am hacking on my own kernel, actually, and just developing my own kernel at the moment. And right now I'm working on user space page fault handling. And it is going very well, I have to say. I'm super stoked to see this. Wow. So this means I faulted that VA deadbeef. This means it's all kind of working, including the part, like, we are successfully able to execute back into user space, prepare the frame, run a bunch of stuff, have this print work. However, right now we are not exercising the code that returns back to user space. we're not exercising all that assembly code I was just working on, because all this does is it immediately just dies, and it kills itself with the destroy syscall. But we at least are able to push the struct onto the stack and jump and divert execution into there, which is pretty sick. Let's keep going. Fault alloc. Let's try it. But also, let's just understand what this does. So we set the page fault handler to handler, and then we do a memory write at hex deadbeef, which is not mapped into memory. That's going to trigger the page fault, which the kernel handles, and is going to defer to this handler, which then queries the utrap frame to get information about it, and gets an error code and a fault VA, which were populated right here. So the kernel gets a bunch of information from the CPU and forwards that information along to user space. Cool. That is very cool. What's the next one? Fault alloc. Let's run it. Okay, fault dead beef. Okay. You should see fault dead beef. This string was faulted in at dead beef. Fault cafe blah blah blah. This, okay, if you only see the first this string line, you are not handling recursive page faults properly. Damn. Dude, I am not even seeing any of this. Also, GP fault. All right, well, time for some debugging. Time for some more debugging. All right, 20-second break to stand up, stretch, and get some water. Be right back. Okay, forgot to put a date on this, so 11/24, this is number 43. I also forgot to take track of timestamps, unfortunately. Okay, so fault out. Let's take a look at what this is doing. This tries to read from hex dead beef and then cafe BFFE. All I'm seeing is fault dead beef. So we get here, and then we don't get any further because there's a general protection fault. Hey, what's up, nameless monster? How much math you know? Because I'm very bad at it. I don't know very much math, which is just the truth. I'm not a math person, really. I know very basic math. Yeah, definitely not. It's been years even since I took calculus, and I get by okay. I think always a bit more math. I mean, a bit more math could be useful, but I don't know. You don't really need to know a lot of math to do what I'm doing right now, that's for sure. GP fault, where is that coming from? Sys page alloc. I think I'm gonna reach for the debugger here. Oops. Yeah, run blank GDB. This is so cool that they already have page outlook. User fault outlook handler. So I'm going to put my first breakpoint at handler. Oops. Okay, now we're in handler. Now we're back in sys page alloc. And my theory is that we are we are GP faulting somewhere within the sys page alloc system call. And let's find out where that could be. It looks like we're actually returning from the system call. So which means I'm going to place another breakpoint immediately after here. And we hit that. So we actually do the system call and return back to user space. File object user fault outlook. And we're actually hitting the SN printf. What does SN printf do? It like writes a string to a buffer or something like that. This string was faulted in. At X. You know what? I think the GP fault is not the actual immediate like symptom. Like the GP faults later, I think what's actually happening is there's like some kind of double fault, which is then producing a GP fault. There's some kind of bug here, which is debug exception, divide error, not interrupt, overflow, bound, device double fault exception. Or maybe I should just directly look at the GP fault. yeah, it's like a little bit hard to, what was the GP is 13. Dude, there are so many ways a GP fault can be triggered. Referencing an entry in the IDT that is not an interrupt, trap, or task gate. So I think that's what's happening. I don't have a double fault handler. I probably should add one, actually. Because I think that's what's actually going on here, but because I don't have that, so it's like, it's misleading. It's like misleading me about what the problem is. I am going to quickly add a double fault handler. Yeah, entry, this is gonna be cool. Y'all are gonna be able to see what it's like to add a trap handler. So double fault is, there's no, or, oh, there is an error code. Handle double fault, and it's gonna be T double fault. T is this call? Ah, there is already one. T double fault. DBL fault. And I kind of always forget exactly how this works, but then I need to go here, DBL fault, and I need to remember all these things. So is trap. I think I'm going to say yes. I don't think we want an interrupt. KT handle double fault and put that at 0 because only user space should not be able to trigger the double fault. And I'm going to find here double fault. Ah, and then what I need another. Do I where are these things declared? Trap. Yeah, that's. Oh wait. Ah wait. Maybe that's it actually. Okay. Does it compile? It compiles. Let me just quickly stash this to separate what I just did from, yeah, but we're not done yet. We need to then go here and dispatch it. Double fault. Handle double fault, and let me come in here. You know what? Or what else? What else could I do? Print trap frame. What do I do on breakpoints? While one monitor TF. I'm gonna do the same thing. Not that the monitor is actually useful to me, but now let's do this and see if we hit a double. We did not, as far as I can see. So maybe that my guess was incorrect. Interesting. Yeah, I don't. Actually, there isn't even a GP fault handler. I don't even have one. All that happens is it hits the default case, which comes in here and env destroys. It prints the trap frame and then env destroys. Unhandled trap in kernel. Okay, so my guess was wrong, I guess. I was somewhat thinking that there were double faults happening. But it doesn't seem like it. So I'm just going to say impl double fault and handler. However, this doesn't actually seem to be used right now. Okay. So back to debugging, then I'm going to actually get rid of this workspace, go back to the original one. Back to debugging then. So so what even happens here? So snprintf does what? Buffer n. It like takes string faulted in at so this is saying, this was saying that if you only see the first string line, it means you're not handling recursive page faults properly. Okay, I'm just going to try this one just for fun. User check assertion failure for via deadbeef free end. It seems like that actually is working. Fault alloc bad. What does this one do? It tries to pass an invalid address, tries to make the kernel print out. It tries to make the kernel access the address deadbeef and print that to the console. But the memory access comes from kernel mode to a bad address. And I actually, the kernel should just, this is what's going to happen. Like it's not going to involve any of this fault handling infrastructure. This is going to get caught simply by this user mem assert in cputs. And that's it. So that is not actually testing anything too interesting. Make sure you understand how these behave differently. It's not only, but all types of processor exceptions that code running in user space can generate. To a user mode, wow. So this is basically saying challenge. Make your kernel do user space interrupt handling in general. User space trap handling. Take all exceptions that are received and bubble them up to the user mode exception handler. That's cool. That's a cool idea. Okay, but this is not working. This string was faulted in at blah, blah, blah. I don't understand. Oh wait, that's okay. I was kind of overlooking what this big if statement even does. So we register a page fault handler. We attempt to do an invalid memory read from a specific address. That faults triggers the kernel, which triggers us. We go and print a message. Then we actually map memory, which succeeds in our case. And then so now we actually have memory there. We actually can properly write bytes to it. And it seems like that would work. So what I'm not understanding fault. What? Fault cafe buffer? I don't understand. So I understand how you can see this. That then what I'm not understanding is where this cafe C0 thing comes from. Okay, because it's going to try to write off the end of a page, which is going to require faulting in another page. I see. All right, 20-second break. Be right back. I see. So this is going to try to read off the end of a page and straddle onto the next page. So it's going to fault as it hits the first page, the end of it, and then it's going to handle that, alloc the first page, start trying to snprintf at that end of the page. The snprintf is going to go and cross the page boundary and page fault as it hits the next page, which is going to, again, trigger a recursive frame. And ideally, that should then map the next page and return back to the caller, which is the snprintf, as it continues That's like hardcore, okay. And this is not working for me. I don't even see the first one. So maybe I'll just comment this out. Something is going wrong here. So I'm not even able. I need to simplify. So I'm not even able to do this sn printf. I wonder. Equals 0. A. Right. What about this? Am I even able to write a single A? To this address? That would be a test. No. Am I able to panic? Yes, I am able to panic. Am I able to do nothing at all? C puts hello. Oh, what's up, Space Pekka? Are you still following the MIT exercise? Yes. Yes, indeed. I am following exercise 11 and 12 from lab 4. Still doing that, and I probably will be doing that for quite some time. What are the arguments here? Size and a length. Oops. Font alloc. 3. I know that the 3 is not right, but that did work actually. It was able to print stuff out, and then we fail on the return. So I am guessing that this is also going to fail. Yes. Okay. This is... Okay, let's debug this then. Let's debug this. So clearly, we are not returning properly. Okay, let's hop in the debugger. And I want to debug user space. So I'm going to we're debugging the handler. So I'm going to file user object user fault alloc yes b handler continue. Okay. So we just finished the handler. That was pretty fast, but we just finished here and exited. And now we are in that assembly code that it seems like I messed up. Let's just clean this up a little bit. Now we're here in this assembly code. And let's just do this as, right. So actually what I want to do is I'm going to add some code that dumps the trap frame. Dump u trap frame cf void dump u frame. That's u trap. Come on, man. All right. Yo, hey, Ismail. Thanks for joining. Hope you're well too. No, it's all good. I'm doing some coding, and I'm doing some debugging because the coding apparently was buggy. So let's, yeah. I want my macro. I had this xprint macro that was very useful. Name u name xprint. This is super useful. I can just do utf fault va eip e flags, oops, esp. Yeah, so the reason I'm doing this is because I'm here in the debugger and I want to confirm that these assembly instructions that I've written are fetching the correct data. And I want to be sure what the actual original data is, because it's possible I have bugs in here that are jumping all over to the wrong place. Okay. Let's run it again. File, user, object, user fault, outlook. Yes, yes. B handler, continue. Next. Oh, dang. I did not print them as hex. Ouch. Let's try that again. User fault outlook. Yes. Did I type this wrong? Oh, oops, file. User fault outlook. Yes, yes. B handler. Yeah, I should script this or something rather than typing it out every time. Error code 4. EIP. That is interesting. EIP 670. That's faulting somewhere within C printf. Am I within C printf? This is going to be such a long function, I think. And how do I? It's in VM printf, so close enough. What is the error code again? TF, which is the trap frame's error code. What's the error code? Trap page fault. Yes. Right, page faults have an error code with this format. Wait, what? Okay, 0 supervisor, 1 user. So this is saying, so we have an error code of 4, which is saying it is a user access that is a read to a non-present page, which is all correct. That is all correct. This program is trying to do a read from hex dead beef from user space, and that page is not mapped. So that and the stack is somewhere. So that all checks out to me. So now let's fast forward a little bit through things and we get back into the assembly. And yeah, so here's the assembly code that I wrote, and maybe it's buggy. Let's see. Page fault. So what's the first thing we should check? I was attempting to read the ESP field. Or no, I was attempting to read the EIP field. So let's take a look. So nice and easy. ESP, right? There's our ESP. Let's examine at ESP plus 40. Okay, that. Let's just dump ESP, even better. Okay, why is there so many dead beef strings? So offset 0, UTF fault VA. So, oh, I didn't do the add yet. Let me do a step I. Okay, now let me dump ESP. That's more like it. At offset 0 should be the fault VA, And that's what we see here, the dead beef. Now let's check out this 40 thing. And that's this hex 670. So that's correct. I wanted to read the EIP field. And that's what we're doing. What about 48? That is the ESP. So that is all looking great. I think I did this correctly. I want to be brave enough to keep stepping. So now I'm subtracting P EVX. So now, and now it's 4 less than this, and now it's 14, so that's good. I'm gonna be brave enough to keep stepping. So now we're getting into it. So let's dump ESP again. And yes, we're gonna pop off these two things, and following that is a bunch of the general purpose registers. So we're gonna step I, and now let's dump the stack again. And now we have all our general purpose registers. We're gonna pop AL. And now let's look at our stack. And now we're pointing at EIP, E flags, and ESP. EIP, E flags, or wait a sec. E flags, yeah, 886, 86, and ESP. So that's all solid. So, I mean, the one thing I haven't confirmed actually is I guess these exact numbers, but I don't know if there's anything I could do about that. This is the straight up information we got from the CPU about the state at the page fault. So yeah, so here we are, and now I'm going to do two things. I'm going to push ESP plus 8, which is going to be this thing, which is the stack. Step I. Let's take a look. Yeah, so now our stack address is here. Going to push. Oh, that's the mistake. That is the mistake. Or is it? Wait a sec. I did not take into account that this push is going to actually change something here. But yeah, that's going to... that's going to be incorrect. What I wanted to do is like, okay, ESP is pointing right here. I want to push the UTF ESP, so I go +8, and then I want to push the UTF E flags, which is +4. But I can't, the 4 here is wrong, because as soon as I push the UTF ESP, it pushes another thing. It pushes another thing, and that means I need to adjust for this here, for the state of the stack after pushing this here, which is, wow, that's like very subtle. That should be an 8, because now I push L8 and that pushes another thing, and so now my stack pointer something is pointing, you know, like 1 here, but I want to access E flags, which is going to be the offset will be the thing I just pushed, UTF ESP, and the IP after it, and that will get me to E flags actually. Count the previous instruction. Okay, that did not work. Okay. Yeah, and what's kind of funny, so with the bug, I'm computing the offset incorrectly. What I'm actually doing is I'm making it so that instead of E flags being loaded into E flags, I'm loading EIP into E flags. And that is probably what's causing the GP fault actually, because I'm probably setting a bunch of bits in eFlags that are not allowed to be set or whatever. And that is going to concretely crash on the pop F when we try to load that into eFlags. Assembly is elite. Assembly is definitely elite. I'm trying my best. All right, 20 seconds, be right back. Word. Okay, this is exciting though. I am super interested to see what's going to happen. All right, let's come back here. So now we've fixed that subtle assembly bug. Yo, what's up, muscle nerd? Hello. We fixed that subtle assembly bug, which means we are going to be able to return from our handler. So what I'm thinking actually happened is actually this char adder A thing was working. The problem is in returning from the handler. Let's run it. Moment of truth. Damn, what the hell? Damn. Wow. So, breakpoint? What? So at least we didn't GP fault, but now this is really broken. What we're seeing here is, so okay, we have the original fault. We were trying to return to user space, and we used to GP fault in the process of doing that and just like crash. Now we don't do that anymore, and it seems like we are returning into some like very weird state that's causing other page faults and other bad memory accesses. This is crazy. So first we hit the dead beef. Apparently we return from that and try to access 20 million or whatever, which page faults, which we like, apparently we handle and return back from that and start executing some other code which causes a null pointer dereference, which we apparently handle that, and that causes an FFFFFFF fault. And that's where we panic because user space is not allowed to map memory that high. That is wild. Wow, that is crazy. You know, I always wondered what it was like to be a kernel developer and have your like returning back into a process go wrong, because it seems so subtle, and that's what we're seeing right now. Like shit is just not working. Like the ideal world is we seamlessly return exactly back to the state of the process exactly as it was, and the process had no idea we faulted and stuff. And that's just not happening. We are like trying to do some stuff, and then we are returning back into like some weird state that is just like crashing, which is kind of exciting though. So I am inspired enough to keep going a little bit more today. Let's get back into the old debugger. File obj user fault outlook. yes, yes, be handler, continue. Okay, here we are, freshly in here, and we have the actually, where are we? Oops, yeah, we are actually not right. We are actually here, yeah. Okay, whatever. I'm just going to next, step I. Okay, now I'm going to print out, dump the stack. We got our stack frame as usual, and I'm going to start stepping. But actually here is a bit of a sensitive sequence that I didn't actually verify previously. This whole sequence of things. Let me make sure I'm doing this correctly. So I moved that into EAX. Now we're at the sub, and now we're at the key instruction. Let's EBX. Let's print these things out. So I'm moving EAX into the memory to be dereferenced at this thing, which looks totally correct, because what I want to do is write EIP into ESP-4. ESP is this minus E18 thing, -4 is 14, and the EIP value is 80670. So that all looks totally correct. What I'm going to do is I'm going to dump EBX. I'm going to dump EBX, which has zeros in it, and I'm going to step I, and do that one more time, and observe that EIP has been correctly written there, so that's good. So I've just confirmed that this sequence is correct. And I am going to just keep going, because I think, so X, 4X, ESP. So we've just pushed. True. That's also the bug. I don't want to push ESP, actually. I want to push this ESP-4 thing. Damn. What? Okay. Wow, I want to push this ESP-4 thing that I computed up here. That's why it's not working well, because I am slightly misaligning things. My goal is to cause execution directly at EIP. I have this little diagram. My goal is to point ESP at EIP and then do a ret such that EIP gets executed and the stack gets repaired to exactly the same state. What I'm accidentally doing is I'm pointing ESP not at EIP but a little bit higher. Oh, wow. And I actually don't really know how to fix that. I cannot use the EBX register because I've already restored all the general purpose registers and clobbered it. But maybe Is kernel development what you hoped it would be? I have to say I'm very happy with how I've been approaching it. I'm actually really happy with this course and how it's guiding me through things, which makes sense because obviously it's meant to be a course to help people learn things. But actually, yeah, I kind of hoped with kernel development I would really learn much more about CPU modes and virtual memory and interrupt handling and stack switching and context switching and all this stuff. And I do feel like I'm really getting a lot of experience with that. So I would say so, but yeah, good question. Thanks for asking. So now we have a bit of a challenge, but maybe we can solve this. So my initial thought was, okay, before this, we do our memory movement way early because we need some intermediate registers. And after we do the general purpose register restore, we can no longer use general purpose registers. So let's do that before. Then I thought, okay, let's do the stack setup after we do the general purpose registers, because doing this general purpose register thing requires moving the stack pointer up 8 and then doing a pop AL. And then I thought, after we do that, we can then just do some more pushes. But like reordering a little bit. But we can't, yeah. And my idea was that we would simply be pushing data and slightly reordering things on the stack, basically. But the kink here is that we can't do this. It's not a simple matter of pushing this ESP value back onto the stack in the order we need it. We need to do this ESP -4 computation, which requires at least doing some E-flags arithmetic, which is not allowed after... but we haven't gotten there yet, actually. But we don't have EBX anymore. And I can't use any general purpose registers anymore. Okay, so my quick idea I'm just thinking of right now is we do a bunch of this math in order to allow us to not do more of this annoying math and stuff in the future. Let's save the result of the computation on the stack. So in particular, we're trying to do a push L of EBX. Oops. Save UTF ESP -4 on the stack for later. This is what we need. So we're going to put, so it's a little bit tricky because we're going to do this computation, move this thing into memory. We're going to cache this value and save it onto the stack and push it even one more. We're then going to need to adjust this to be 12 and take into account this new thing plus this thing plus this thing, and then do the pop AL. And then I want to actually subtract store USB to original state. This is a bit wild. I'm just moving ESP all around like crazy. So then my idea was restore ESP back to there. You know what? Or we can actually we can do negative offsets from ESP anyway. Maybe let's do that. Maybe that's actually kind of a clever way to do this. So rather than doing this, so ESP is going to point at EIP. And we actually want to reach all the way back there for this value we pushed a long time ago, which is going to be 44 bytes lower. Because, okay, hear me out. So push regs is 32 bytes long. This pack is 8, so that gets us to 40. And we have our one EBX pushed thing even below that, which is 44. And that sort of nicely caches the computation. The downside is that we're actually kind of using a little bit more stack space than I would like to. An optimal solution here would not require too much extra stack space. So a more optimized solution here would actually be to reuse the stack space for these two variables. Here I am intentionally preserving them actually, because I add 12 to move the stack pointer a little bit higher past them. And then I was adding 12 and then subtracting 12, which preserves them. But actually we don't need to do this. We can actually clobber that memory. Thinking in SM is so dope. Yeah, I mean, it is kind of fun. It really, it's very creative problem solving, and it's kind of an interesting game to play, basically. A more optimized solution would be to reuse the stack space of these two variables. So for example, I don't actually, so instead of the push L, I'm just going to do it because I feel confident enough to try. Instead of this, actually, you know what? Before I do this, I'm going to stage these changes. What is it? So push EBX, add 12, pop, subtract minus 44, and then go. So I think that will work. What I am going to bravely try is implementing my optimization. So after we do this, or we can even do it way earlier even. Although, wait a sec, this relies on the particular, these offsets rely on this particular state. So we do all that stuff, we don't disturb that. After we've done our memory write and stuff, we then add ESP plus 8, which pops these things off the stack. And then we do push LEBX to push our cached value onto the stack in the place where UTF error lives. And then we don't need to do this anymore. Actually, just kidding. We do need to do this, but it's only going to be 4 now. So then we push this thing right now. We're going to temporarily kind of undo that and increase the stack pointer to skip over that. So our pop AL will be pointing at the right place. That is going to pop us all the way up to EIP. At which point we then do this relative read down, but it's not going to be 44, it's going to be 32 plus 4, which is 36. We're going to read from that as the ESP minus 4 and push. interesting. Yeah, it's like ESP is right here. Our value, our cached EBX value is going to be in this UTF error slot. We're basically going to push that and clobber this push regs region with one thing. And then we do a push out 8 from ESP. Okay, I'm going to kill the palm tree because I'm like really into the flow. Okay, so that pushed one thing, clobbered the first kind of the end of this push regs slot. We still want to get the E flags, and so we dereference 8 offsets from that. And that should be correct. All right, I am gonna try this. Let's go. This is pretty fun, actually. I'm actually quite enjoying this. You know what, and I'm not even just gonna run it. I am going to go back into the debugger and just carefully watch this work, I think, because I'm really hopeful that this is going to work. Yes, 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 be handler, continue, next, 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 step I, okay. So we're here, and we're going to print out these things. EAX is our EIP, that looks right. EBX is our -4, it's like the 14 value. This is the DE18. We want to be 4 bytes below that. So that looks good. We're going to examine that slot in memory. It's the 14, and it's zeros right now. We're about to execute an instruction that places the EIP value into this slot. Let's execute that. And we can observe that that EIP value is now placed into the ESP -4 slot, which looks good. We can now now we're doing this add stuff. So now we're doing add plus 8 minus 8, just to clarify. Yeah, so we had these two values. It was the default VA and the error on the stack. And we've done an add 8 to get rid of them, which is what we're seeing here. It's just the 0, deadbeef 0, deadbeef O thing. So that looks correct. We're going to push EBX. And now let's look at the stack. So now we have our cached value with the DE14 there. And that's nice and saved, and we'll be able to reference that later on. So we can avoid doing any use of general purpose registers and also any use of math or arithmetic instructions which would alter E flags. Okay, what's next? Then we're going to temporarily add 4 to ESP to temporarily skip over the cached value, which we've now done. Now we are pointing at pure E flags. We're going to execute the pop AL, which loads all of that into the registers. And now we're sitting here at the push L -36 ESP, which I want to quickly dump lib pf entry.o just to confirm. Pop a minus hex 24 36. Yeah, so this is pushing dereference ESP -36. So let's dump our stack one more time. So now we're pointing at the EIP, E flags, and ESP. EIP, E flags, ESP. We're about to push the ESP -36, which is the cached value, that 14 value from last time. So let's do that and check our stack. And it's right there, DE14, perfect. We're going to push L8 from ESP to get the E flag, this 86 value. Step I, examine the stack. This is looking good. E flag's on the bottom, followed by the ESP-4. And we are set up perfectly for the pop F, pop L ESP ret. I feel like I'm a sports announcer or something like that. I'm like, like we are set up perfectly for blah, blah, blah. Okay, let's do the pop F. E flags is currently 86, step I. E flags. I guess E flags never changed. Pop L ESP. Okay. Currently ESP is this EBFF 0 thing. Step instruction. And now ESP should be that 14 thing. Perfect. That's what I like to see. And the last thing to do is ret. And we're pointing exactly at the EIP we want to execute. So I'm going to step instruction one last time. And with that, we are going to leave this transition stub and hopefully seamlessly resume execution exactly right back into wherever it was executing in this C printf call where it originally faulted. And it looks like we're there. I'm just going to continue. Check. All right. No, you're fine. So that worked. It may not be clear what actually happened, but we did not get a GP fault or anything. We printed out HEL, which, let's check it out. Which comes from right here. So the fact that we see this HEL means that the program tried to read a string from an invalid memory address, the deadbeef. The first read of the first byte at hex deadbeef triggered a page fault, which the kernel forwarded execution to this handler. We dump the utrap frame, print out fault deadbeef. We allocate memory at deadbeef, actually, kind of behind the scenes, and that is actually it. And we return. We return into that assembly stub we just walked through, and which I just debugged and fixed. And that transitioned us smoothly back into the C printf routine, which kind of got restarted. And now it's actually able to read those bytes, which are just going to be zeros currently. Under the real thing, we're actually going to put some data in there that's going to be read out by cprintf, but for the moment we didn't do that. So there's going to be all these zeros in memory. This thing is going to kind of just do nothing because it's trying to read a null, like a null C string. And we're going to finish off and print out the first 3 bytes of the string hello, because that's what I did, and print out. So now that that's all working, let's get it. Let's re-enable this and see how this goes. Here we go, moment of truth. Common stream W, thank you. Check it out, fault deadbeef. This string was faulted in at deadbeef. Hell, exceeding gracefully. So that's good. That means it's working. That means, so instead of like last time, it kind of printed nothing here. It just had this like empty line and then hell. Now we don't have the empty line anymore because we were able to fill in that memory. It was trying to read from invalid memory. That attempt faulted. We allocate the memory, slide in some data, and then retry, and then revert execution back, and print it out, and then trigger hell. So the only other thing left to do is add this back, which will be interesting because this is going to trigger the recursive fault. And it's possible that there are still other bugs that are going to make this not work, but I'm like kind of hopeful. All right, moment of truth. Let's run it. Let's run it. Okay, I think that actually worked. The reason it kind of didn't immediately look like it did is because I have this dump trap frame thing. Let's run it again. Yo, check it out. Let's check this thing out. What do we see? You should see fault dead beef right here. This string was faulted in a dead beef. Fault cafe buffer. Fault cafe C1000. This string was faulted in a cafe buffer. Exiting gracefully. Yeah, I'm gonna call that a massive win. We totally debugged the sketchy assembly code and got it working. And it seems like we have user space page fault like pretty working, including support for recursive page faults, which is sick. So I'm gonna call that a huge win. I would appreciate dubs in the chat. You got this big dubs, thank you. Coming out with this assembly, and I barely understand it. Yeah, man. Yeah, you will someday. Feel free to let me know if you have any other questions about that. I can try to answer them at some point. But by the way, I mean, if you want to understand this stuff better, I would seriously recommend going to Pone College and probably like what exercises, like the exercises that will help you understand what I did in today's stream are going to be, I mean, these are maybe a little bit even more advanced, but it's going to be any of these exploitation exercises on Pone College. Maybe program security. I mean, shellcode injection, program exploitation. Yeah, probably this. So this is what I would recommend if you feel like you didn't really understand everything I just did, like you were like kind of lost. The skill set I was using there is basically like kind of like a software exploitation kind of skill set where you're kind of using assembly instructions and using assembly that like redirects execution in very surgical ways. That's exactly the life of an exploit developer. So yeah, thanks Zara, confetti emoji. Look at my school project. Yeah, totally. Yeah, I mean, yeah. Whenever you have time or motivation, yeah, this is what I would recommend reaching for. All right, y'all. That was cool. I'm gonna stop there. Thanks a lot for joining. Yeah, when is GB host me when I am on? Okay, awesome. I'm glad to hear that. I'm very glad to hear that. Yeah, GDB foo. Like I'm not using any of these GDB like helper tools. Like there's a lot of them out there, like Peta GDB or whatever. There's a lot of these tools that kind of give you like these really nice like stack dumps and like all this stuff. Like those are pretty cool, but I'm just kind of doing it old school and raw. So Shivang, you're late. I'm about to end the stream, but nice to see you again. Thanks a lot for being here. Yeah, unfortunately, I am about to end the stream right now. Damn, missed all of the stream. Yeah, unfortunately you did, but and it's pretty unfortunate because this is a good one actually. I think this one might have been one of my absolute favorites of like debugging and writing a bunch of kind of like hardcore assembly code and seeing that work. So, all right, y'all. Thanks a lot for being here. I really appreciate you. We're at 43 weeks now. Like we're getting close to almost an entire year of weekly streaming, which is kind of crazy. Yeah, thanks, Jivang. Nice. Yeah, I'm gonna end the stream. Thank you for being here. I have my Discord if you want to join and hang out. Subscribe to my channel if you like what I'm up to. I do this every week. Like and comment and And thanks a lot. I'll see you next time. Peace. Have a nice week. Stream.